Question 2. Using the information shown in the graph, determine the speed of the cut B at 5 seconds. So from the graph here, we can determine that the speed of the cut A after the collision, after start leaving the cut B is 1. Huh? Using the conservation of momentum, the mass the cut A is 1,000 kilogram times its speed before the collision is 5, huh? Equal to that mass 1,000 times the new speed is 1. It has decreased from 5 to 1. Okay, and momentum of the cut B, which is 2,000 kilogram mass times the speed, and therefore we can determine the speed of cut B here easily. Huh? 1,000 times 5, 5,000, 5,000 minus 1,000 here is 4,000. 4,000 over 2,000 is 2. Huh? 2 meter per second. Answer is 2. 1 point. So only 1 mark. So we don't need to write a very long answer like in the scoring guideline. Only one simple equation like this. Question 3. On the following grid, draw a smooth curve on the velocity of the cut B as a function of time. It should be, you have to calculate a few value. Similarly, the speed of B at the time 0.5 is 2, which is here, 2. The initial value is 0. Huh? You need to determine the speed of B at some other time, such as at 0.1 second, at 0.2 second, at 0.3 second, so that you can draw the correct curve. Okay, using the speed of the cut A at those times. For example, choose the point that is easy to read the value, huh? Such as this point. When the speed of the cut A is 3, we have 5,000 minus 3,000, huh? And then divide 2,000. This is the speed of the cut B at the time here, 0.25 seconds. Okay, so this is 2,000 over 2,000. That is 1. Speed is 1, which is here. Okay. Find one more value of the speed B at another time. Huh? 2 more value to be, accurate when drawing the graph. When the speed of the cut A is this value, 4.1, huh? Well, 5,000 minus 1,000 times 4.1 and divide 2,000. Huh? 5,000 minus 4,100 and then divide 2,000 kilogram, huh? 0.45. Oops. 0.45. 0.45. 0.5 here. 45 is close here. Okay. So the curve goes up like this, and then I don't know if it starts curving down a little bit like this, huh? Okay. So the point to answer this question correctly is calculating a few other velocities at different times. Okay, yes. Using similar equation like this. Next one. So let's check the answer. Here, calculating about 3 or 4 values, huh? And then you can draw the curve accurately. You can go up to some like inflection point, yeah, and then like that. Calculate some value, the VB at different time. Actually, you can write the equation for VB, huh? And that VB is 5,000 minus 1,000 VA at a time t, and then divide 2,000 kilogram mass of the cut B, huh? Is the equation, and that equation results in this curve graph. Question B, for the time from 0 to 0.5 seconds, the velocity of cut A can be described by the function here. Calculate the magnitude of the maximum net force acting on cut A during this interval. The question is force. How does the force relate to the given velocity function? Force, what does it have to do with velocity? Force is mass times acceleration. And what is the relation between acceleration and velocity? Derivative velocity, dv over dt, huh? E acceleration, and then times the mass to get the force. So the maximum force is when this derivative, the acceleration here is 0, huh? that is the maximum or minimum. Actually, you need to draw, you have another condition. The force is maximum when this differentiation dv over dt is 0, and the second derivative d square v over dt square is maximum is smaller than 0, huh? But anyway, when taking this derivative, you have a quadratic function, and it's that quadratic function is acceleration. A is dv over dt, huh, which is 64t cubed minus 48 t squared plus 5 derivative, which is 3 times of 64 t squared minus 2 times of 48, which is 96, huh, t. This is quadratic function, so the graph of acceleration is like this, huh? So the acceleration is minimum here. We don't have the maximum, huh? Because this is a greater than 0 coefficient. Okay.
Yes, yes.
Minimum. We don't have maximum force. Cut a function like that. This is minimum acceleration. So that minimum force, not maximum force. How do we find maximum force? Here, this is a 192. 3 times of 164. 64 here is simply 192, huh? 192. Setting the derivative of the previous derived expression for acceleration to be 0, we can find the time at 0.5. But when that thing equal to 0, we have minimum acceleration, not maximum. That's weird. Right, this graph is a concave up parabola. Just note 192 t squared x squared minus 96 x. Yeah, change the there. This is the minimum acceleration, and the minimum value is when the time is 0.25, huh?
Yes, yes.
We do not have maximum acceleration, or the maximum acceleration is when the time is 0.5 in the given domain. 0.5, huh? Here, this is the time 0. This is 0 time. And the minimum acceleration is, of course, we can determine that replacing the time to be 0.25 seconds. The minimum acceleration is 0.12. Okay. It's 0.12 meter per second square. But this 0.12 negative acceleration, we just need to take its magnitude. It results in the maximum opposite force, huh? Which is 12 here times the mass of the object. Okay, so anyway, we take this negative value to calculate the maximum force, huh? Okay.
Yes, yes.
That's just opposite force, yeah, which is the opposing force acting on the cut A when it collides with the cut B. Yeah, in opposite direction. Yeah, the collision. Okay. So the force is maximum when A here equals 0. 192 t equal minus 96 t for 25 seconds, and the minimum acceleration, actually maximum value in magnitude is 12, huh? And A, meaning the minimum value in equation, is minus 12 meter per second square. Meter per second square. And so we can ignore this one. So that the maximum force is the mass times this maximum acceleration. The mass of the cut A is 1,000 kilogram, huh? Times 12. So that results in 12,000 Newton. The next one, questions B2. On the following grid, draw a smooth curve of the magnitude of the force acting cut A is uniform function of time. Clearly indicate the values of maximum force on the vertical axis. The acceleration is a concave up but we just need to take the value of the acceleration. This is a minimum minus 12. The force, we just care about its magnitude, not the negative sign. Huh? Therefore, the force is maximum at pole 25, which is 12,000. We can do 12,000 here. Huh? Okay, and then you need to do some more calculation to determine the acceleration at the time point 1 and point 2, so that you can draw the correct curve, huh? The curvature of the curve. Okay.
Yes. Yes.
Parabola, which is opposite to the acceleration, because we only care about the value of acceleration. Not smooth. Okay, calculate the acceleration at the time point 1 first. Point 1, replacing point 1 in here. 192 times point 1 square, and then minus 96 times point 1. Huh? We have this is the acceleration, and then we need to time 1,000 from the mass, huh, to get the value of the force. 7,700, about that. 7,700. Okay. Let's check how many boxes here for 12,000. 1, 2, 3, 4, 5, 6, 7, 8. Okay, 8 boxes for 12,000. So 7,000 is how many boxes over 12,000 first, huh? 12,000, and then times 8. We have 5.12, huh? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 5 here, and 5.1 is here. 7,680 Newton. Okay, at this point. So we need to draw the graph through this point. You need to calculate 1 or 2 more values, huh? So that the curve that you draw is accurate. And then curve down to 0 when the time is 0.5 seconds. The foam is removed from the cut A, and experiment is repeated. Removed from the cut A, repeated. The cut collide with both cut A and cut B having the same nature and find the velocities as in the original collision. Remove the foam. Same initial velocity, meaning 5 meters per second for the velocity of A here. So without a foam, the curve, the graph can be different from this curve. Can be a steeper curve, like the color, like this one, like that, happening in an even shorter time compared to when we use the foam. The time interval during which the cars are in contact are different. It's supposed to be shorter time, shorter than 0.5 seconds, because there's no foam. Okay, the foam will increase the time. And in the collision without the foam, the cut A is in contact with the cut B for shorter duration. There, I said shorter duration. Okay, shorter duration than in the original collision with the foam. For the original collision, when the foam is present, the magnitude of the average force exerted on the cut B is F1. For the collision without a foam, the magnitude of the average force is F2. What is the relationship between the magnitude of the average force F1 exerted on the cut B for the collision with the foam and the magnitude of the average force F2 exerted on the cut B for the collision without a foam? Very long question, but it's just asked for the relationship between F1 and F2 with the foam F1 and without the foam F2, huh? And the answer is that F2 is greater than F1. Yeah, because the time is shorter. We have the force either change momentum over time. So this shorter time results in greater force. That's why without the airbag and the seatbelt, it is very dangerous for driver when an accident happens, because the seatbelts and the airbag will increase the time of collision when the accident occurs, and therefore increasing the time will reduce the force acting on the driver. Okay. And so we say that the force F2 is greater than F1, so that the force is greater, F2 is greater than F1, because the force is the rate of the change in momentum, which is the ratio between the momentum change and the time. Without the form, the collision times is shorter, resulting in greater force. For the same momentum change. Question lastly 2. No, this is question 2, not the question 1. Continue, Okay, let's see if we can do this question 2 here. Yes, we can. And it seems not very difficult, Okay, we have the 2 springs. Do this one. Derive an expression for t as a function. Okay, let's read the problem. The student conducts an investigation to determine the relationship between the period of oscillation t of a system consisting a block and n attached spring n equal 1, meaning 1 spring. The student starts with the block of mass m attached to a single ideal spring of the spring constant k, as shown in figure 1. The student holds the block so that the spring is neither stretched nor compressed. At the vertical height 1 meter above the motion detector, the student releases the block from rest and records the period of oscillation for the system consisting of the single spring and block. An additional identical spring is attached in parallel in the figure 2, and the procedure is repeated for n equal 2 springs. This procedure is repeated through n equal 10 springs. Derive expression in t as a function of n, the number of springs. Express your answer in terms of m, k, n, and physical constant as appropriate. Expression for period. Period, simple harmonic oscillation. Check the formula sheet. Formula sheet. Simple harmonic oscillation. I'm looking for the equation here. The period of the simple pendulum Ts is 2 pi times the mass m over the spring constant k. Okay, just use that formula. T of the spring constant is 2 pi square root of the mass over k. The spring constant k here depends on the number of spring. For this is the total spring constant of system. If it has only 1 spring, then it's 1k. If it had 2 spring, then it's 2k. 3 spring, 3k. 4 spring, 4k. So with n spring, you times n the number of spring, because those springs are connected in parallel to each other, and therefore the total spring constant is simply the sum of those spring constant. Okay, so you just need to times k for each spring with the number of the spring n. Okay, so we have the final formula, 2 pi times m, the mass of the object, divided by nk, and we ignore the mass of the spring, given that the spring has negligible mass, very small mass compared to the block. Okay, so yes. This is the formula, this is the answer, easy to that. Answer question 2. Maximum force, magnitude 12,000, The graph, not accurate as my graph because I calculate one value. They didn't calculate. Okay, question 2 here. Nk, that's it. M over Nk square root. Question B, on the following axis, get the graph T is a function of n greater than 1. This is the equation. So how do we plot the graph? Use the calculator, And then the calculator will show you the type of the curve of the graph. You need to find the x-intercept, y-intercept if they exist, and the inflection point or the maximum and minimum. Okay, the function is a constant 2 pi times the square root of the mass m, which is a constant. Let's take the constant like 10, the mass, 10 kilogram, for example, over number n, which is x, and then k. K is also a constant. Let me make it like a 2 or 100. Let's make it 2 to look, check for the graph here. The graph is a curve like this. So does it has the asymptote? The horizontal asymptote is the x-axis, and vertical asymptote is a vertical axis. So the graph looks like this. No numerical values are required, just a curve, exponential curve. See, the student plot the data for t square over as a function of number of spring n as follows, as shown. Okay, we have the equation that I wrote above, which is t equal 2 pi square root of m over nk. So doing the square on both side equation, we have 4 pi square times m over nk. So this is an inverse. Let me put all the values, 4 pi square m over k as a constant in front of it, and then times m to the power minus 1. And therefore, we have this straight line graph. Draw the best fit line. Okay. Draw the best fit line of the data and draw the best fit line. It depends on your scale. Here the link to the document and on the calculator as well. So try drawing the best fit line later and check it with the answer. The questions and the answer here. Remember that the best fit line goes in between the points